Hello, today we're going to go over Chapter 7.2 of AP Chemistry. We're going to talk about the nature of light. So light is a type of electromagnetic radiation. The visible light that we see is just a tiny portion of the full spectrum. So it goes all the way from these long waves over here. We have microwaves, and then on the high energy end, these tiny wavelengths would be gamma rays, the highest energy form. So microwaves, right here in this kind of low energy section, it causes the molecules to rotate or spin. So when we put something in the microwave, the radiation is the waves are what causes the water to spin around, and that's what's going to cause your food to heat up in the microwave. Their kinetic energy is transferred to the molecules around them, which increases the temperature. Visible light causes electrons to become excited, which means they're going to higher energy levels. We're going to see them jumping up to a higher energy level. And ultraviolet light has enough energy that it's able to actually break bonds or reform new bonds or eject the electrons. So that's why we have sunscreen right here for this ultraviolet light, because it's able to damage the bonds within our cells, which then would cause skin cancer. So ultraviolet light causes bonds to break and reform. The equations that we need for this section are, we're going to be able to find the wavelength, which is the distance between the crest of the wave of two adjacent waves, or you can do trough to trough as well. And then we have the frequency. This is the Greek symbol nu for frequency, which is how many of these pass by per second. So these would have a lower frequency, less of these wavelengths would pass by per second. Over here, we would have a lot more passing by in each second since they travel at the same exact speed. Okay, so if the wavelength is high, then the frequency is low, and vice versa, because they're going to multiply to always give us this constant, which is the speed of light, 3 times 10 to the 8th power. Okay, a second equation that we can use is to calculate the energy of a photon of light. And we're going to use Planck's constant, which is this number right here, joules per second. And we're going to multiply that by the frequency, joules times seconds. We're going to multiply that by the frequency, which is measured in hertz or per seconds. And that's going to tell us how much energy is in the photon. If we wanted to relate the wavelength to the energy, the shorter the wavelength, the higher the energy. Basically, what we would do is rearrange this equation and solve for this lambda. So we would have C over nu, and we would plug that in down here. So it would be H times C over nu. Okay, or in other words, you can put these two equations together, plug in what's given in the equation to solve for the energy of the photon, okay, or the wavelength. The Bohr model is the idea that the electrons go around like planets going around the sun, which is not completely correct, but it is very useful. So we're going to do the Bohr model of sodium and chlorine and see how that might be useful for us. Sodium has 11 electrons, so we need to know how many they have, and chlorine is going to have 17 electrons. The nucleus is tiny, and we're not worrying about it right now. So this is energy level 1, energy level 2, okay, and energy level 3. So energy level 1, we remember from 8th grade, it holds 2 electrons, and honors chem. Energy level 2 can hold up to 8 electrons. It has s and p orbitals. So there's 2, 3, 4, 5, 6, 7, and 8. So the total now is 10. We have one more electron, and that's going to go in this very outer ring. So that is what gives sodium its one valence electron. It has one outer electron in the 3s orbital. Okay. So this actually does tell us a lot, even though it's a very simplistic version of the atom. Chlorine has 17, so we're going to have energy level 1. And actually, chlorine has more protons in the center, so it's going to pull the electrons a little bit closer. So I'm going to draw them just a little bit closer to the nucleus here. Okay, there's a greater attraction to the nucleus. So energy level 1, energy level 2, energy level 3. And let's add our electrons. So we have 2 in the first energy level. We're going to have 8 in the second energy level. There's 4. There's 6. And there's 8. So we have 10 total. We have 7 more. And this third energy level will hold all 7 of those. 4, 5, 6, and 7. So this one has 7 valence electrons. And this one has 1 valence electron. And that's why, whoops, I wrote those backwards. That's why these guys go together so well. Because to be stable, valence electron, to be stable, they would like to have a full set in their outermost ring. So having that full octet of electrons for the S and the P block is going to make them lower in energy. And that's why when you put sodium and chlorine together, sodium will, it doesn't have a great attraction to that electron, so it will lose its electron to the chlorine atom. And that's what these Bohr models help us to see. So these are the Bohr models of the atoms. Okay, so they show us just a really general view of the energy level and the distance from the nucleus of those energy levels. We're going to see that that's not quite the case, but it is still helpful. Okay, so hydrogen is a very simple atom because it only has 1 electron, and so it's just going to occupy that first energy level. We're going to look at the absorption and the emission spectrum. We're going to talk a little bit more about it in a second. Quick preview. For hydrogen, it has just 1 lonely proton and 1 electron orbiting that proton right here. Okay, and there are empty energy levels. I'm going to draw that electron a little bigger so we can see it. There are empty energy levels surrounding this that the electron could potentially jump into. Okay, we'll pretend those are circles. So any added energy, and this electron is going to end up jumping up to a higher energy level. And eventually it's going to come back down. So the idea of going from energy level 1, I drew it to energy level, let's number them, 2, 3, 4, to energy level 4, this is absorption. So it has to absorb energy in order to go to a higher energy level. Eventually it's going to fall back down. When it falls down to the second energy level, so all the transitions to the second energy level actually give off light that we can see, and that is the emission spectrum. So energy level 4 going down to energy level 2 is emission, and that's going to give off light. Okay, and we're going to be able to see the light that's given off, and it's going to have distinct wavelengths based on the energy. So we can calculate the energy of that photon with our equation from before. And remember, this is the Greek symbol nu, which stood for frequency. So we can calculate the energy. And let me go ahead and do the other one. C equals lambda times nu. So with this other equation, if I wanted the wavelength instead of the energy, I can solve this for wavelength, which is going to equal, sorry, this is not helpful. What I wanted to do is solve for nu, which is C over lambda. Okay, so if I was worrying about this wavelength here, I can plug this, since it's equal to lambda, I can just plug it right in there and get rid of that, and I will have the energy is equal to H times C over my lambda, so I can relate the wavelength to the energy, and you can see it has an opposite relationship. As the wavelength increases, the energy is going to actually go down because you're dividing by a bigger number here. Right. Okay, so the quantum model of the atom It's kind of like giving our address. So we're going to have multiple parts that tell exactly where we are at in the city and even in the state. Okay, we're going to skip over these guys for a second. You guys can go back and read about them in your book if you would like. So first off, an orbital is a three-dimensional region around the nucleus that has the probable location of an electron. So that's why we sometimes call it the electron cloud, because it's this area where it might be found. Quantum numbers are the address of the electrons in the atom. So they're going to tell us the distance from the nucleus, the energy that it has, the shape of the orbital it's going to take up, the orientation, and then the spin. Okay, so this is a little bit more than you need to know for the AP test. The AP test will only cover the principal energy levels. Okay, and so it's going to cover this number one, and also the shape. So the energy level is represented by a lowercase n, and it's going to tell us how far away from the nucleus we are. So when I drew my circles a second ago when I was doing my Bohr model, the circles are the energy levels. Okay, so we had energy level 1, we had energy level 2. That's the principal quantum number. And the total number of electrons in one of those shells or energy levels is equal to 2 times the energy level squared. So for example, let's do 5. The number of electrons that fit in the fifth energy level are 5 squared, which is 25, times 2, which is 50. So the fifth energy level can hold up to 50 electrons, and that's because it has S, P, D, F, and even potentially the weird one that we won't talk about, which could have G. Okay, so it can hold up to 50 in that fifth energy level. We don't usually go above 4 in AP Chem, so you don't need to worry about that. Angular momentum is just the shape. So remember, S is a sphere, P is that figure 8 shape, D kind of looks like a flower, it has 4 lobes, and F is a very strange shape. We will look at those in your book on Thursday. The magnetic quantum number tells you the orientation. So let's talk about P really quickly. So the P orbitals, we have 3 possible orientations. Okay, so that's this quantum number, the orientation. We have an X, a Y, and a Z. So P is the most simple. That was the shape is P, and that is this kind of figure 8 shape. Okay, where it has 2 lobes, and it can be in the X, Y, and the Z orientation. So we could have P sub X, which might look kind of like this. We can have P sub Y, which might look like this. And P sub Z is the one that comes out towards us and then goes back. So we're going to draw a dotted line for the one going back into the board here. Okay, so these are the orientations. Now, in an atom, they are all overlapping. So you would put them all together and you would get this weird shape where it's coming out at you guys and going back. And when we overlap a whole bunch of these, we basically get a sphere. So that's why we think of the atoms as being this kind of spherical shape that's supposed to be a sphere. It's hard to draw dotted lines on this thing. Okay, so when we overlap all these different orbitals, it basically forms a spherical shape. Okay, how many orientations can the s orbital have? We just said the p orbital has 3. The s orbital is just 1 because it's a sphere, so no matter how you rotate it, it's going to look exactly the same. And then the f orbitals are really strange. You just kind of have to remember that there are 7 of those f orbital orientations, and for d orbitals, there was 5 orientations. Okay, and then lastly, spin. What you need to know is one is going to be spin up and one is going to be spin down, and that's it. Here's a general summary of those shapes of the orbitals. So this is S, it's a sphere. P is the 2 lobes, and D is the 4 lobes, and then F has like 8 lobes, and it's very crazy, and it's not on here. Okay, and the one that you really have to worry about is the energy level, and then just a general idea of the shapes, and mostly just S, P, and D. All right. I hope you guys have a wonderful day, and I will see you tomorrow.